Welcome everyone to AI Horizons, the podcast where we explore the cutting edge of artificial intelligence and its impact on business and technology. Today, we're diving deep into the fascinating world of LLM agents, large language models acting autonomously to complete complex tasks. We have a fantastic panel of experts with us today to unpack a really novel approach to making these agents smarter and more capable. We've got perspectives from business strategy, deep machine learning, agent architecture, data optimization, and real-world implementation. Let's jump right in. So LLMs are showing incredible potential as agents, moving beyond just text generation. But training smaller, specialized agents efficiently is a major hurdle. What's the typical approach, and where does it fall short?
Well, the dominant method recently has been rejection sampling fine-tuning, or RFT. It's elegant in its simplicity. You start by showing the agent examples of an expert, like GPT-4, succeeding at a task. The agent learns to mimic that.
Exactly, then in later stages, the agent tries the tasks itself, and you only use its successful attempts to further fine-tune it. It's an iterative process of exploration and refinement based purely on positive outcomes. Think of it like learning by only studying correct answers.
And a key appeal is that it avoids the complexity of training separate reward models, which can be quite cumbersome and require lots of hyperparameter fiddling. RFT is, well, simpler.
But that simplicity comes at a cost, particularly in complex environments. RFT tends to get stuck. It inherently favors tasks where the agent or the initial expert can easily succeed. This means the really tough subtasks often remain unsolved. They stay out of distribution or OOD.
We see this constantly in practice. You train an agent, it gets good at the basics, but hits a plateau. It's like teaching someone to drive, but only on empty parking lots. They never learn to handle busy intersections or tricky parallel parking maneuvers. The agent masters the easy stuff and avoids the hard parts.
Okay, so if only learning from success leads to agents that shy away from difficult problems, where do we find the missing pieces for teaching those harder skills?
This is where the research gets really interesting. The authors of the paper we're discussing looked at the rejected data, the failed attempts by the expert model like GPT-4. And surprisingly, these failures weren't just garbage.
Right, even when GPT-4 failed overall on a complex task, say in the WebShop environment trying to find a specific product, its failed trajectory often contained really useful steps. Maybe it navigated correctly for a while or identified key product features, but then made a mistake later on.
We saw this clearly. For instance, a task might require navigating multiple pages using next or going back if an initial selection was wrong. RFT-trained agents often failed to learn these navigation skills because they rarely appeared in the successful, simpler trajectories it focused on. But the failed GPT-4 trajectories, they often tried these actions even if the overall attempt failed.
That resonates deeply. In engineering or product development, postmortems on failures are often more instructive than celebrating successes. It's that classic heuristic, isn't it? Fail fast, learn faster. Analyzing why something broke reveals the path to making it robust.
Learning from failure. It feels intuitive, yet counterintuitive in standard ML training. How does this new approach, exploring expert failures or EEF, actually harness these failed attempts without, teaching the agent bad habits?
That's the core innovation of EEF. It doesn't just treat the entire failed trajectory as bad. Instead, it simulates starting the agent from intermediate states within that failed expert trajectory.
Let's break down the EEF process a bit, following their algorithm 1. First, like RFT, you do behavior cloning, supervised fine-tuning, SFT, on the positive expert trajectories to get a baseline capability. Standard stuff.
Then comes the exploration phase, which has two parts. Part 1 is like RFT, the agent explores the initial tasks. Part 2 is the novel bit. It takes those failed expert trajectories and simulates the agent taking over from various points within them. maybe starting halfway through the expert's failed attempt.
And here's the clever part: analyzing those simulations. Imagine the expert failed after 10 steps. EEF might simulate the agent starting from step 5 and step 8. If the agent succeeds when starting from step 5, but fails when starting from step 8, EEF infers that the expert's actions between step 5 and step 8, while part of an overall failure, were actually beneficial for reaching that successful intermediate state at step 5.
So in the reinforcement training phase, EEF selectively trains the agent only on these identified beneficial action sequences from the failed trajectories. It uses a masked loss function, LSFT, so the agent learns, say, steps 5-7 from the expert's failure, but ignores the later steps that led to the ultimate failure. It's like sifting for gold nuggets in discarded mine tailings.
Hold on a second. This simulation and labeling process, it sounds smart, but how robust is it? Are we sure we're identifying truly beneficial actions or just lucky sequences within a failed attempt? Simulating from intermediate states might not fully capture the context. Isn't there a risk of reinforcing subtly wrong strategies, a kind of sophisticated cherry-picking?
That's a fair challenge, Expert 6. It's not a perfect oracle, absolutely. The simulation provides evidence, not certainty. If starting from state SI leads to success, and starting from state S, J, later in the same expert trajectory leads to failure, it strongly suggests the actions between SI and S, J were helpful in reaching SI, or that S, J represents a harder state the agent needs to learn to recover from.
And crucially, EEF also focuses on identifying recovery states, points where the expert made a mistake, but then took actions to try and get back on track, like the back to search example in the paper. Learning these recovery maneuvers is vital for robustness, and something RFT often misses. EEF specifically looks for trajectories where the agent can succeed from such a recovery state and trains on those recovery actions.
So it's a probabilistic approach, acknowledging the noise, but aiming to extract signal from those expert failures. Does the evidence back it up? What did the experiments show?
The results are, well, pretty striking. On WebShop, a notoriously difficult e-commerce simulation, the EEF-trained agent achieved a 62% win rate. Compare that to standard RFT hitting around 53.6% and the original expert GPT-4 only managing 35.6%.
And they report similar significant gains in SciWorld, another complex environment requiring multi-step reasoning. They claim to be the first to break a score of 0.81 in WebShop and 81 in SciWorld with this approach, which is a significant milestone if validated.
Wow, okay. Let's translate that. Expert 1, from a business perspective, what does 62% win rate versus 35% for GPT-4 mean strategically?
It means a lot. We're talking about potentially taking a smaller, much cheaper to run model like Llama 3.8b, applying this EEF technique, and getting performance that dramatically surpasses the giant, expensive model like GPT-4 on specific, complex tasks. This opens the door to deploying sophisticated agents for specialized functions where cost, latency, or data privacy concerns previously made using the biggest models prohibitive.
Absolutely. Beating the expert model with a fine-tuned smaller one is the holy grail for many teams. It means specialized agents become economically viable for a much wider range of applications. The performance jump isn't just incremental, it looks potentially transformative for certain use cases.
The paper also mentions something intriguing, using data from an even weaker expert, GPT-3.5 Turbo. How does that fit into the EEF picture, especially from a cost perspective, Expert 1?
Now you're hitting on something critical for business adoption. GPT-4 is powerful, yes, but the cost per token the API calls, it adds up incredibly fast, especially during the data generation phase. If EEF allows us to extract significant value even from the failures of a cheaper model like GPT-3.5 Turbo, which is roughly 30 times cheaper according to the paper, then the economics become incredibly favorable.
And the results support this. The EEF GPT-3 and 4 variant, which incorporated GPT-3.5 failure data, performed even better on WebShop than the one using only GPT-4 data. This suggests EEF's filtering mechanism is robust enough to handle the noisier, less optimal actions from a weaker expert, while still benefiting from the sheer volume and diversity of experience that cheaper data provides. It's not quite garbage in, gospel out, but maybe.
It speaks to the efficiency too. The comparison in Figure 3 is telling. EEF achieved better results with fewer exploration simulations, controlled by the M parameter, compared to just running standard RFT more times with different settings, RFT-XN. You get more improvement for your compute buck during the exploration phase.
Okay, EEF sounds powerful, efficient, and potentially cost-effective. But let's bring it back to Earth. What are the practical challenges, the catches? Expert 5, what hurdles would you anticipate deploying this in a real-world business setting?
Well, first, setting up that simulation environment isn't trivial for every task. WebShop and SciWorld are designed for this, but adapting it to bespoke internal business processes or more open-ended web tasks requires significant engineering effort. You need that ability to restart interactions from specific states. Second, while EEF might be more efficient than alternatives, the exploration phase itself still requires considerable compute. Simulating multiple trajectories from multiple states across thousands of subtasks, that's not free, it's an investment. It's like tuning a Formula One car. The end result is peak performance, but the tuning process itself requires specialized tools, data, and expertise.
And defining success or failure robustly can be tricky outside of benchmark environments. In real business applications, outcomes are often nuanced, not just a binary win-loss. How does EEF handle tasks with partial credit or multi-objective goals? That needs more exploration.
And I'll throw in my contrarian note again. We're seeing great results on these specific benchmarks, WebShop, SciWorld. But are we optimizing for the test? How well does this intricate process of learning from simulated slices of failure generalize to truly unpredictable, open-ended real-world scenarios where the state space is vastly larger and the definition of failure is fluid?
That's a crucial point, Expert 6, the difference between benchmark optimization and genuine intelligence. It highlights the need for ongoing research. Where does this line of work go next?
The paper itself suggests several avenues, refining how beneficial actions are identified, maybe using binary search within the failed trajectory instead of fixed intervals, integrating EEF ideas into more sophisticated search algorithms like Monte Carlo tree search, MCTS, using the expert failures to guide the search branches.
There's also potential in using preference learning techniques like DPO, but feeding it only the identified beneficial action segments from failures as the chosen data, and perhaps other parts as rejected. This could offer a more direct way to instill the desired behaviors.
From a strategic standpoint, the big questions are, how do we optimally blend data from different experts, high cost, high quality versus low cost, lower quality? How do we apply this beyond web tasks to robotics, complex planning, scientific discovery? And critically, how do we build and maintain trust in agents that have explicitly learned from failure data? Explaining that to stakeholders is a challenge in itself.
Fantastic discussion. We've journeyed from the limitations of learning only from success with RFT to the surprising potential hidden within expert failures, explored the nuts and bolts of the EEF technique, weighed its impressive results against practical challenges, and looked towards the future. It seems EEF offers a compelling, more efficient way to build specialized LLM agents that can tackle harder problems, potentially even outperforming their giant expert counterparts while being more cost-effective by cleverly learning from mistakes. As Expert 5 put it, analyzing failure is often the key to robustness. A huge thank you to our panel of experts for sharing their insights today. This is clearly an area with tremendous potential and ongoing evolution. That's all the time we have for today on AI Horizons. Join us next time as we continue to explore the frontiers of artificial intelligence. Thanks for listening. This paper introduces a method, improving how language model agents learn. The method explores failed attempts made by expert models. It helps agents learn valuable skills even from expert mistakes. Standard training often uses only successful expert examples. One such method is rejection sampling fine-tuning. This approach struggles when experts fail on complex tasks. Many difficult problems remain unsolved during training. The new method analyzes trajectories where an expert model failed. It identifies beneficial actions or plans hidden within these failures. The agent simulates starting from intermediate states in the failed expert attempt. If the agent then succeeds, the preceding expert actions are marked beneficial. The system selectively adds these beneficial action sequences to the training data. It carefully avoids learning from the parts of the trajectory that caused failure. This technique helps the agent solve previously unsolvable tasks. The approach was tested in complex WebShop and SciWorld simulations. It significantly outperformed standard fine-tuning and the expert GPT-4 model. The method achieved a 62% win rate in WebShop. It also exceeded a score of 81 in the SciWorld environment. These results set new state-of-the-art performance levels. Agents trained this way learned better navigation skills like using next or back. The method effectively used helpful data, even from a weaker expert model. This shows potential for using less expensive expert guidance. Exploring failures offers a simple way to enhance agent training. It relies only on standard supervised fine-tuning techniques. Future research could improve identifying beneficial actions. Combining this approach with search algorithms is another possibility.